Okay, now the recording has started. I just talked about administration. Okay, and this Kramer's rule. So one, yes. So if these are the formula, if this A determinant is not zero, then you have a solution. If it is zero, but this other delta determinant is non-zero, then there is no solution. If everything is zero, then zero or infinite number of solutions might exist. Okay, so this is just one example again, but perhaps you understood, all of you understood the Kramer's rule. We have a system of linear equation, and the coefficients forms the A matrix, and the other is the vector. I checked whether there is solution. I calculate the determinant of this. I did it actually last time, so it's minus 39. It's non-zero, we are good. The first delta, I should have right here not D but delta, doesn't matter. Here I changed the first column for the beta. I calculate the determinant again, and when I do this operation, I got the result. In the same way, I construct the next determinant. I calculate the value. The result is 1. And for the third one, I change the last column. And then I got the third results. So it is interesting. If you can calculate determinant quite quickly, you have an algorithm, for example, then it's okay. And you can fix linear equations quite quickly. These are with 3 unknown, so these equations. But it could be 100 or 1000. It often happens, and I don't know who learns IT. Some of you learns IT, and you should learn later. What is the name? Something about algorithms, ordering, shorting, short things, or selecting things. And you will have a calculation if you have an array, for example, and it has n elements, and you double the number of the elements. How slower will be the algorithm, for example, a shorting? If it's double time, you double the size of the array, and the length of the running time of the algorithm is double, that's fine. It's 4 times longer, that's a problem, and it's 2 factorial or something like this, then that's wrong. You will be able to calculate later whether you use this Kramer's rule or you do something else to fix linear equations. I don't know how understandable I am, because I had done this, and this is something that you will learn in the future. Yes?
Are you talking about the big O notation?
What is it?
Big O notation, like to calculate the time of an algorithm.
Sorry, the
big O notation.
Order?
Big O.
What is big O? Big O,
like,
yes, that one. Ordo or order. Okay, let's jump. So the last thing that we will learn before the test is this vector space. Actually, we have learned about them. Just we haven't. So we haven't gave it a general definition. You have a set, and There are typo and everything. Oh, doesn't matter. I will correct it. So you have a set, and it is a vector space about above the real numbers. If there is an operation, the following features. Be careful, it's not plus, it's not adding, it's an operation. It could be just asterisk or sharp or anything. That's just a sign. And this operation has some general feature. One is this, the first is, bless you, commutative stuff. The order is not important. Then there is distributive. You had something similar. And now the following is more important. You have a zero element, and this zero element, it's null vector here. If you add to any vector, then you got the same vector. This is plus. But if you can change this for the add, so this operation. If you change it in your mind for multiplication, product, then for the product, this zero element is the, what is the name? The unit, the ID, so the one, because if you multiply any vector with one, and then got that vector. Do you understand what I want to explain you? This is something general, more general. You will learn algebra, not linear algebra, general algebra, and you will learn these things. And the last one, if you have a zero vector, then you can define this type of element. I just call it inverse or inversion. It's something general. The inversion is usually with multiplication, but here we use this sign. But this is here a sign. It's a special function. It's V times V goes to V. It's an operation. It's not the add. The adding and also the multiplication has the same features, but this is something different, more general. Okay. Additionally, that should be familiar. There are the following features. The following features says for scalars. I said scalars, but these are not real numbers. Are for the multiplication with scalars, there is a what is the name? Associativity. There is a distributivity for the multiplying scalars, vectors, and scalar sum of scalars are multiplying by a vector. It's also distributive, and also you have this unit vector. Now here it is written vector. It is written scalars, but it's more general. Okay, these are true for two-dimensional and three-dimensional vector spaces, but vector spaces could be general, so it could be a finite number of multiplication. And, yeah, other typo, it is good for polynomials. And here, yesterday, I was struck. You are from different countries, but in my country, the mathematical education secondary school, so the level of the mathematical education here in Hungary decreased in the last years. So, do you know what is a Cartesian product of two sets? You know? Yes? With the others? No? You know? Okay. Then it's okay. It's fine. Just okay. I'm talking, and when I'm talking, I suppose that you know what I learned in secondary school. The problem is that I didn't know. I spent more than a decade abroad. It changed. For example, 2 weeks ago I got to know the Hungarian pupils don't learn logarithm and exponential in the secondary school. Actually, they learn it, but they don't need to pass an exam. We have a final exam at secondary school, and you do not need to pass mathematics and physics anymore. And then you can come here and study linear algebra in Hungarian. Okay. The Cartesian product is a very very simple thing. You have two sets, and you forms all ordered pair. That the first element is from the first set, the second element is from the second set. This is an example. There are one set. These are first names, John and there are family names, Smith, Turner, Carpenter. The Hungarian version is Kovács, and doesn't matter. You do this Cartesian product, it's cross, it's not multiplying, it's cross, and then you construct the following pairs. John Smith, Ann Smith, John Turner, Ann Turner, John Carpenter, Ann Carpenter. These are pairs, one from the first set, one for the second, and you take all of them. So if, for example, you have the coordinate system, and you have a line x and y, and the sets are the numbers on one axis and the other axis, and you this multiplication, you got the plan, you got the coordinate system. That's trivial for those who have learned it, but it's something big jump who hasn't. This cross, this Cartesian product, can be considered as operation, and it has features, many. I didn't write it because that's a homework to check what operations you have, but if you don't know it, I don't know. It's difficult to understand what I'm saying. Which is important, this Cartesian product could be could be generalized. You can start with two sets and pairs, but you can continue with three sets and triplets. Then the definition is say the Cartesian product of sets A, B, and C is such a set that consists of ordered triplets in which the first member is an element from the set A, the second member is element set B, and the third is set C. And you can go until 100 or whatever you want. Okay, it's typical. I have the same problem when I teach Python. Polynomial. Do you know what is a polynomial? Yes, you know. Okay, great. You know. Okay. Do you know here? Everyone know what is polynomial? Everyone. Okay. The polynomials could have one unknown, one variable, or more variables. So I jump back, and now you can understand what I'm saying. So this okay, okay. It's very quick. In secondary school, that what I explained was the material for 45 minutes class. So the set V is a vector space above R. If there is an operation which has these rules, then the operation has these features. That's okay. And this could be, say, for 2-dimension, 3-dimension, and n-dimension. Just it should be finite dimensions, so not infinite dimension. And you can say the same for polynomials, and the polynomials are this is the sign of the polynomials. I have a very bad feeling this will be something ring or something like this. Okay. What I'm saying is quite simple. You have met with it. You have met vectors, set of vectors, but this is something general. If you have a vector space and that vector space has a subset, it's also a set, it contains vectors too. And we call this subspace if this L has the operation above the L, that's same. That's are the same operations like the V had. For example, you have the coordinate system and you decide to take half of the coordinate system on one side of the xy plane. Then that will be a subspace. Is it understandable? You have the coordinate system. This is a vector space. If I can put vectors here, whatever I run, these are triplets. And I just take this half, then that's a subspace. If you have this L non-empty set, and then it is a linear subspace if and only if the following conditions are fulfilled. This one. Actually, this is the linearity, but in general form. So if you have an H subset of this V vector space, and you have to consider those H sets which subset of the V and contains H. You look for the minimal size of this subset, and this is then you can say this H is is generated okay. So you're looking for the subspace that has minimal size and contains this H subspace. The other statement, it is a subset of all subspace containing H set, and you have a sign for it. And always exists a minimal subspace, such a subspace. If you have this H set, then this is the general system of the V vector space. If this equation is satisfied, it's important that the number of the elements. We say that the V vector space is generated finitarily if it has a generator system containing a finite number of elements. This is not finite number, it's infinity, because I can consider the real numbers, I can consider the other numbers, so it's always infinity. So it's not that one, that's the finite has limited number of elements. So if this vector system, these are now vectors, is a general system of finitely generated V vector system, all elements could be written as the linear combination of V1, 2, and vectors. And now we are arriving somewhere. We learn about linear combination, linearity, linear dependence, independence, a lot of things. And now we are defining, we give the definition of this again. Someone took this watch. Just I don't see.
If you click one.
Thank you. I didn't sleep so much. Okay. We have an A vector, and coordinates x0, y0, z0. Then it's very, very familiar. This is x. It's a normal vector. The direction is the same with the x-axis, and the length is 1. I have the same for the y, and I have the same for the z. So you can write this in this form. Okay, I did it. You have a vector space. The vector space are here everywhere, but I selected this subspace with 3 vectors. Their number is finite, 3, and you can write any vector as a linear combination of these 3 vectors. That's the same we written for the first 2 or 3 classes, lectures. It's very similar. What was the problem with your credit transfer?
I was a high school student, so technically I don't have any credits.
But you tried. You went to the register office.
Can we talk about it later?
Yes, we can. Just it's difficult. Yeah, we can. Okay. General comment. So here at the university there are some problems. One problem is the different level of knowledge of the students. I do this, or I do Python programming. One student can write very complex programs. The other have never wrote a single line and don't know nothing. And what can I do in this with this? I cannot give a good talk which is satisfying for both of them. Okay, doesn't matter. Yes. So this actually not but a linear independent generator system of the vector space is the basis of the vector space. This is it. So we have vectors from a subspace, and this is a special one. I could extend it. I add 4th dimension, and then of course in the 4th dimension I don't know, I use W, and it's the coefficient will be 0. But this is one of them. Also there are a lot of things that you can do. Doesn't matter. So you have this basis. Okay, so if you have this vector space and you have subspaces that we call bases. For example, I can change the direction of these vectors. I don't know, I have an Fy, then Fz, Fx, Fz, then this A minus okay, so these are different subsets, different bases. All these bases has the same cardinality. It means the number of the elements in the set, the bases are the same. And for this case, this number is free, and we are in the free dimension. So this common element number, this cardinality, element number of the basis of the vector space is called dimension. It could be 0, 1, 2, 3, 4, and then 1000 or whatever. Yeah. Yes. We have this system of vectors b1, 2, 3, n. This is a basis in this V vector space, and we have an A vector which is part of this V vector space. We have some scalar numbers, and this A vector can be written in this form. I feel short. Cannot, doesn't matter. Actually, this is not rocket science. This is it. Yeah. That's the same. Absolutely. Sometimes it's funny because I'm explaining the trivial, but everything should be defined and deducted in mathematics, and also physics. Physics is more difficult for this. There are special physicists, mathematical physicists. They try to do with mechanics, with quantum mechanics, with thermodynamics, the same that the mathematicians did. They use definitions, deductions, sets, and mathematical deductions to define and understand the different physical parameters. For example, entropy. One of my former professors did the thermodynamics without entropy. I mean mathematically. This is very funny because you do not understand anything from those books and deductions. Okay, so you have this system of vectors, the basis. You have a vector, you can write the vector in such a form, and then these numbers, these lambdas, are the coordinates of this A vector in this basis. Also, I brought two different bases here, this F and E. Yeah. If you have a V vector in 2 dimensions, that is not a 0 vector, null vector, or in 3 dimensions, okay. Then this set is the line which is crossing the origo. Wow, we discovered the trivial again. And the next step, you have 2 vectors, and you are not in 2 but 3 dimensions. These vectors are null vector, and these vectors cannot be written in this form. I mean, these are not form a line, not parallel, and they are not in the same line. Then with two scalars, you can set a plane which crossing the origin. This is also very well known, and the first line that is equivalent with this definition. If you have a normal vector with n 1, 2, 3, and you have a point with p 1, 2, 3, then the equation of a plane with this normal vector which crossing a point is this. But it is well known. But here we wrote much more difficult to decrease the usability and understand and make it less understandable. Of course, I'm kidding. This is the general stuff. Okay, if you have a set which defined in this way, and the vectors u1 to m are linear independent, then L is subspace of sorry, something is not odd. Yes, okay. I just cannot read my type. Okay, so we have a set which is written in this form with scalars and vectors, and it's a linear subspace defined and not defined, generated by these vectors. If these vectors are linear independent, then this set, this L set, is an n-dimensional subspace, and there is a typo at the end of the sentence. In this case, the set, this key set with another vector is an affine subspace. That's the name. And all affine subspace can be constructed with this form. From this subspace, adding a vector, then you got another subspace. Okay. That's interesting. The Minkowski set. There are two interesting things in them. No, this Minkowski sum of these two sets A and B is this. You just add these elements, and one element from the first set, the second is from the B set. And the operation is that we have defined before many slides ago. The other thing, the name Minkowski. Have you ever heard this name, Minkowski? Yes? Familiar? You learn physics? Yes? You also. He was a originally Polish mathematician, and he did a lot of things, One thing was okay, there are the special relativity. It was made by Albert Einstein. It's not really true. The general relativity theory was made by Albert Einstein. There are a special relativity theory. There are reference system, and if two reference system is resting, comparing to each other, or the speed is constant, then it has relativity theory. That's the special relativity theory. And the more difficult is the general, when the reference system could accelerate and there is gravitation. That's the original and very good work of Albert Einstein. But the special relativity theory is work of more people, Poincaré, Minkowski, Albert Einstein. And Minkowski, Einstein published the results, and it was very, very difficult to understand. There were 3 space coordinates, and there was 1 time coordinates. And in Minkowski, put them together, they had vectors with 4 elements, and did all deduction and everything that Einstein did, and he is also a father of the special relativity theory. So this is a familiar name, this Minkowski. It has no importance for the test or anything else. That's, I think, that's something interesting, at least to me. But for a IT student, perhaps it's not so important. Okay. Okay. You can also add together the subspaces L1 and L2, and this is an additional subspace. Yes? It was too difficult, or doesn't matter. Okay, so so this is the sum of the subspaces, and this is the intersection, like at the sets. And if you have this sum and the different subspaces are disjunct, or not disjunct, so the intersection is only this null vector, then we say this is a direct sum. Okay, there were many definitions, really many definitions. So let's see something else. Okay, I give you some exercises. Have you looked in it?
Yes.
Are those exercises easy?
A little.
Okay, that will be the test. And two other tasks.
Will the two other tasks be about capital spaces?
Yes. So tomorrow we will learn how to do some exercises in that topic, but not today. Okay, if you don't have any questions, then I think I dismiss the class for today. Tomorrow we will continue, and before the weekend or during the weekend, I will give you more exercises for the rest of the tasks. Okay? Okay. Thank you.